get you started on impulse. Impulse is ELR 2.7, where you define and calculate, and then you're going to also make the relationship to momentum. So for impulse, all you really need to know is that impulse is the same as saying a change in momentum. So let me show you what I mean. For impulse, I want you to imagine this car being pushed by this fellow here. The car is just sitting there, not moving at all, so it has a velocity of 0, and it has a mass of 1,000 kilograms. So it's a pretty hefty car. In order to change the momentum of this car, I think we can agree that to make it go from no momentum to something else, change it, you have to apply some kind of a push. So on your paper, I need you to fill in the blanks with the red text. In order to change the momentum of something, you have to apply a force, a push or a pull. But what we're going to be looking at is what happens to the amount of push that's required from you. Like, how hard do you have to push if you do it for more or less time? So this guy right here, if he were to give this car a really hard push for just like a second, would that change the car's momentum for very much? Like, would it roll very far? But if he was to do that same really hard push for a longer time, I think we can agree that that car is going to get going with much more momentum. So impulse is talking about, like, yeah, it requires a push, but it requires a push combined with some amount of time doing it. The time matters when you're giving it a push or a pull. So let's break this down and see if we can make it into an equation. We're going to say that if you're giving this a 60 Newton push for 10 seconds or a 60 Newton push for 30 seconds, that makes a big deal. How do we calculate that kind of a thing? Like, how are we going to figure out how much momentum this car is going to have as a result of these two different types of pushes, like pushing really hard for short or pushing really hard for long? So here's how we're going to do it. If we start out with what we just talked about, to change momentum, you have to push or pull a certain amount of time. This is actually already in the format of an equation. So to change momentum, that's like saying a change in momentum is whatever you end with minus whatever you started with. That will tell you how much it changed. So to give you an example, say that you start with 10 kilogram meters per second of momentum, and then you had a push, and you end with 20 kilogram meters per second of momentum. So if you ended with 20 and started with 10, 20 minus 10, you went up 10. Your change was 10. So that's where this comes from, ending minus starting. On the other side of the equation, the part where in order to change momentum, you must, on the other side, a push or a pull for a certain amount of time, well, that's a force times time, force multiplied by time. So now we're starting to get closer to an equation, and it actually looks like this. So this is the triangle shape. This is called delta. It's a Greek letter. All it means is the change. So if you say delta P, that means the change in momentum. Remember, we use a P for momentum. So that's the left side, the yellow side of this equation. Change in momentum equals how hard you push on it, the force, for how long you push on it, the time. So this is our equation. Delta P equals F times T. So I want you to please label these things. The left side, we call that the change in momentum requires, and this is what impulse is. So when I ask you to solve for the impulse, it means solve force times time. So if I push on a car with 300 newtons of force for 10 seconds, 300 times 10 is my impulse that I've added to the car. And that impulse will tell me how much the momentum is going to change. So let's put this into action. If we want to do an impulse equation, there are two ways to do it. The first we're going to talk about is by removing momentum. So you can use an impulse to slow something down. And the first way we're going to talk about this is, what happens if you have a really big force? If you have a really big force to slow something down, it means it's not going to require very much time. And hopefully this kind of makes intuitive sense. If you have a car that's going super fast and you apply a gigantic amount of force to it, well, it's not going to take long to make that car slow down. Let's use some numbers. Suppose I have a car with 800 kilograms and it's cruising along at 4 meters per second. We've already done momentum a bunch. The momentum for that is mass times velocity. I calculated it for you. It's 3,200. That's the momentum of the car at first. So you can see it's going fast, my little streaky fast lines. But then it slams on its brakes. And when it does that, it stops in just a half second. So it's stopping really quickly. And as we already know, something that is stopped has a momentum of 0. So we went from 3,200 down to 0 in just a half second. So the thing that we're going to solve for is, well, how much force did that take? So here's how we do it. We get out our equation. It's also up here on the corner of your screen. The change in momentum is equal to the force times the time. Well, our change in momentum was we went from 3,200 down to 0. Well, that's easy. 3,200 down to 0 is a change of 3,200. We don't know the force yet, so we're going to leave it as an F. But we do know the time. It said that it stopped in just a half second, so we plug in a half for time. Now all we've got to do is divide both sides by a half so that we get F by itself. And this, I often see people multiply by a half. That's not correct at all. If we're going to divide both sides by a half, we end up getting 6,400 newtons of force. So if you think about this, here's what it means. In order to stop this car in just a half second, for that entire half second, every bit of it, you would have had to push this hard in order to make the car come to a stop. So now let's talk about a different way to stop this same car. What if we'd have the exact same car, 800 kilograms, going the exact same speed, or velocity, 4 meters per second, so it has the same momentum. But this time, we use a really teeny force, and we stop it in a big amount of time. So instead of really short time, a half second, we're going to say that it stops in 8 seconds. So this is like you gently press on the brake for 8 whole seconds until the car comes to a stop. Hopefully you can see that if we have the same car, but you're just applying the brakes a little bit over time, well, if you have a big amount of time, it's not going to require you to push very hard. But we're going to find out exactly how much push it's going to take. So we use our exact same equation. The change in momentum is still 3,200 because we're still going from 3,200 down to 0, so that's a change of 3,200. We don't know the force, but this time the time is much greater. It's taking much more time. Same as before, we have to divide both sides, but this time by 8. And when we divide that, we find out it takes 400 newtons of force in order to bring this car to a stop. Whereas before, it took way, way more than that. And it's because if we use 8 seconds instead of a half second, we can just push a little bit for each of those 8 seconds. Since we're spreading out the amount of force required, it takes us less force. So let's just slow something down. Let's talk about making something go faster. This time I have a car we're not going to deal with something that's stopped. We're going to have a car, same car as before, but now this car is moving a half meter per second. So it's just creeping along, moving pretty slow. When I figure out the momentum here, we've got 400 kilogram meters per second. And we're going to say that the car speeds up to 4 meters per second. And it does it in just a second and a half. That's pretty quick. So we're going to go from a half to 4 in just 1.5 seconds. So we're going to go from 400 for the momentum up to 3,200 for the momentum. And this time, because our time is so short, a second and a half is not very long, our time is small. That means that our force is going to have to be really big in order for this to work. So if one is small, the other has to be big, and vice versa. So let's plug it in. Same equation. Our delta P, our change in momentum, is going from 400 up to 32, so that's a change of 28. Our time is 1.5, and we're solving for F. Divide both sides by 1.5, and it turns out that you need almost 1,900 newtons of force coming from the engine in order to speed up that fast. So this is like a fancy sports car, even though it doesn't look it. In order to speed up that quickly, you have to apply a lot of force. You have to have a really strong engine pushing on that car in order to get it to go that fast in that amount of time. So what if you drive a car like me, a junker, with just a few cylinders in it? Well, if you're going to try to get up to the exact same speed, it's going to take you more time. So this is the same car starting at the same amount of momentum, speeding up to the same as before from the previous one, 4 meters per second. But this time, instead of 1.5 seconds, my car is going to take about 6 seconds, about 4 times as long. So in order to do that, plug it in again. It's the same change in momentum, but this time we're going to do it in 6 seconds, not a second and a half. Divide both sides by 6, and my car has to push much less. Instead of that giant number from before, my car only has to push around 470 newtons, but I can get up to the same speed. It just takes me a while longer. It's going to take me 6 seconds of pushing instead of a second and a half of pushing. So now that you've seen these 4 different ways, I would like you to please try these on your paper. Pause the video, write down the numbers that you need, and work out the problems. The answers are sitting on my counter up front when you are ready to check.